And on the sphere, there's just a small hole, what we call almost a point source, that's moving, that has an amplitude. How would you express it? Everywhere else, it's 0, except for that little area. Come on. Okay, you guys are too smart for this. Let's see. All right. First of all, let's say the velocity on the surface, clearly it has a theta dependence. It's axisymmetric, we say, because there's just one hole. And so if I put my axis through it, okay, in other words, if I drew it like that, now can you write the expression? I did that at the very beginning of class. I described what theta is. What is theta here? A point, an angle theta describes a circle. Okay? Now can you tell the answer? Yes? Okay, well, enough torture. So let's, okay. We say that it has a surface velocity when theta is, let's see, yes, less than a certain angle theta 0. And it is, between 0 when theta is everywhere else. Does that make sense? Do you understand what that shows? No? Okay. Let's just. This are spherical coordinates, as you remember. We said this is an angle theta from the z angle, and this point, all points at angle theta are like this. Come all the way around it. That's what theta represents, right? This is something you need to fundamentally understand. If I make theta very, very small, it just represents just a tiny little hole. No? Do you get it now?
I get it.
You do get it? Okay. Yes? Okay, no. Right? Now, why did you not think about this? Nobody is saying, oh yes. Okay, well, I won't belabor the point, but in a different way also one can say theta, because it is so small that we can say it's delta over A, that being the radius of the hole. Okay, or the diameter of the hole, A being the radius of the sphere. So this is the expression. Now that you have the velocity, finally, what's the next point? What can you do? What should you do? What is your next step? And below, what's your next step? What do you do now?
Substitute this in the
Okay, so let's find out the components, the expansion of this in Legendre functions. Okay, I'll do the first part. Now, which M will it be? Can you tell? Can you guess? M. Previously we had 0, we had 1. What will this one be?
More than 1 because there are no distorting angle?
Yeah, it'll be complicated because just like Fourier transforms now, it's not a simple shape. It will involve probably infinite, in fact, infinite number of Legendre functions. Okay, so what we want to do here is, as in the limiting case, where the diameter goes to 0, this also means theta 0 goes to 0, okay? In the limiting case, because we're trying to get the point source expression for it, then we have, by substitution, an integral from 0 to theta 0, or this is same as delta over A, okay? Okay, this is, yes, what one thing you need to remember is when PM cosine theta 0, and theta 0 as it goes to 0, cosine theta 0 goes to 1, and PM of 1 is 1. That's how the evaluation of this comes out. So finally we say yes. Or theta 0 squared. See, this is sub S. Okay, those are the coefficients of Legendre functions that represent a point source on a sphere. So the putting it all together, velocity on the surface of the sphere. So the velocity on the surface far field expression the far field pressure placeholders? No. Yes, substituting into the pressure expression, we have PR theta. Remember now, this is those are the coefficients which we have from up here, and the intensity. Now, this is what I mean by separating the angular dependence, and that usually is called the form function. That's different than the displacement, and the form function in this case is and the power, of course, is obtained by integrating FR theta. Let's see, we have everything. Let me just move from here. To show you the expression. Once you finish it, and we'll discuss it in just a moment here. If you look at the figures in your hand, you see at the top sources placed at this angle. Okay, yes, sources here, and as you go around it, around the sphere. Now at high frequencies, radiation amplitude drops quite a bit. In other words, if you have the sphere here, a high frequency sound is coming from this side. If you go around it, it almost blocks it. Okay, I mean, some sound will come through, but you don't hear it very much, and that's expressed by these. But if it's a low frequency sound, okay, when Ka is small, over here, it's almost nothing. I mean, no effect. Okay, so it says two things. Ka, either the radius is very small, then there's no shielding effect, or the frequency is so small that wavelength is very large. So this part here is the shielding effect, okay? Whereas at low frequencies, it's a transparency. Now, you have a very low frequency on one side, it really doesn't matter. It's as if the rest of the sphere doesn't exist. It doesn't have any barrier or shielding effect on it. Okay? You can see the difference, and that comes from just plotting this. But at low frequencies also only the first term becomes dominant when you look at these. So I'm sure these are all complicated looking, and by looking at it at first, difficult to recognize what term does what. That's why I think it is good to go back to one of those simple cases of vibrating or oscillating sphere. Now there's one thing that there's an example that I'd like to assign as a homework problem, and that's a cap. If you have a spherical cap, and again this is a regular textbook case, and if you have a sphere that has a cap, spherical cap, that's moving in and out, okay? What's the pressure at far field? Now this is a spherical cap. As a velocity U surface, let's call it. Now, this is different than a different problem called piston in a sphere. Okay? A piston in a sphere will have this moving in and out, as opposed to this is a cap that moves in and out in a radial form. All right? So there are two different things. And this is the pressure for this one. And for this, write the expression for surface velocity. All the things that we've been trying to do. You do these, you're in great shape. Okay. Any questions? You'll be mathematically very proficient experts. Okay. With this, we can do a number of different things, but I think I'm just going to stop with the spherical sources here. Other things that we could do, could have done, I'll explain what they are in just a very just examples so that if you come across them, you know, oh yes, I might be able to do this. All of the work that we have done related to harmonic oscillations. Okay, that means some sort of a sinusoidal vibration. What we didn't do are transient or time-dependent, arbitrary time-dependent, or non-harmonic oscillations. Some of the common ones are impulsive, impulse or impulsive motions. And one of which is, again, we use spheres just because mathematically it's easier to handle, and also are quite representative of some of the actual things. Think about even an explosion in the sea. It's basically a radiation, okay, from a sphere. And in this case, you say, all right, the sphere radiation is, or at the surface, or the velocity is u0 at time equals 0. Okay, and otherwise, there's nothing. So it's basically can be, velocity can be a, what's it called, Heaviside function, or its acceleration would be an impulse function. And how would you find the sound pressure that is radiated from it? Another problem is impact problem. Now, you know about these small spheres, ball bearings, right? Steel spheres. And when you hit them against one another, and also this so-called Newton's cradle, right? When you let one go, it hits the other one, and so on. If you have just two of those small ones and let them hit each other, you hear a sound, a clack. Where do you think that sound comes from? What is the source of radiation? Of course it's collision, but very good. But look, if you want to solve that problem, of course, in sound pressure, you have a general expression. What would be your boundary condition? Okay. I want to say a couple of things about it. One is, you know, when you do this, it vibrates. Okay, that vibration, the mode shapes, etc., get involved in radiation. Of course, when you have these spheres hit each other, they're fundamental. Most fundamental vibrations are like 40 kilohertz, very, very small ones. And so you should not be able to hear them. Right? Yes? No?
40 kilohertz.
Mm-hmm. Yeah, unless you're a dog. You're not a dog, so you can't hear them. What do we hear as a clack is sound due to the motion, okay, sudden motion of the pulse, of the ball. In fact, even without an impact, they say in old India, they have these yogis, I guess, it could slap a sound with one hand. In other words, if you can actually stop your hand impulsively, you should be able to hear a clack sound. Same thing with these balls. And the sound comes from sudden acceleration and sudden deceleration. All the air that moves with them, it's called the acoustic mass that suddenly dissipates the sound. Interesting, but these are parts of the transient radiation problems. If we have time in the next several weeks, we can return to them and talk about them, but we're not covering them right now. Okay? Any questions before we move to cylindrical? Cylindrical radiation. Much easier. Much easier, yeah. Any questions? No? All right. Is there a musician among yourselves? Anybody play? No? Nothing? Okay. Not even radio? That's what I used to say when people ask me. All right. Now, John is kind of looking at a problem that's related to, right? How do you determine sounds from rubbing of two hands? Okay, yes, he doesn't know that. Yeah, but he's actually modeling this problem, right? Okay, well, that problem actually is this problem. But you didn't know that. See, when you do this, you see, you hear a sound. How would you model this? What is physically, not him, all of you, physically, what do you think is happening that's causing the sound? Very good, like impact. What is friction? Interaction between two materials, but they have to have something else. Is there friction?
They have to be motion.
In relative motion. Okay, right. Forces generated and energy that's dissipated, depending on how you look at it. Because friction has two components, right? It has two roles in life. One is it generates a force against the other one, and the other one is it dissipates energy. So these are two different but equally important things. So for our purposes, if I ask you to model, can you do this? What is this? No, what do you think is happening here? See, now you know something about acoustics, modeling, etc. Mm-hmm. Mm-hmm. Yeah, essentially that's what happens. So if this is a plate, and the issue here is, see, you hear this, but you hear something different here. And if I make it move faster, it's a little bit different. So you need to be able to characterize, number one, the force that's generated at contact. What is that force? How do you generate it? If you think about a balloon, okay? If you rub the balloon with your hand, if your finger is a little bit wet, then it's a squeaky sound, okay? How would you model that? I think you can model. You're getting there to be able to do that. The key in this case, and in all the cases, to define what you need to know, okay? We said here, see, there's a, you should keep this in mind because this is my own way of looking at problems. In sound and noise problems, I divide them into a force source and an acoustic source. They can be the same, but they can be extremely different. Okay? I wish, yeah, I don't have some props, but the, how should I explain? In a complicated system, there can be, in fact, an engine, okay? You have a cylinder, combustion is taking place, and that's actually the force source. It also generates some sound, but a lot of that energy also, vibratory energy, goes to, let's say, a panel. Okay, that has nothing to do with the cylinder, but vibrating it like that, that's an acoustic source. So in both cases, you need to know how to define these sources. What we have done so far, we have looked at, excuse me, acoustic sources. And I have been pushing you towards how do you describe an acoustic source so you can get the sound radiation from it. But if I had here instead some sort of a force, some sort of excitation, before you get to it, then you need to define how that is generating this surface vibration. For instance, just to make it exciting, for let's say we have the same problem. Okay, but now you have a little cap here, and I say, well, that cap actually is connected to something else with a spring, and I'm exciting it with a force. Well, you know, this is a ship problem. In a ship, you have pumps that are running. Pumps are connected to various parts of the ship hull, and that's vibrating. Now, that's my force source. This will become my acoustic source. Okay? So I need to know the amplitude of that in order to be able to do this. But to get that, I need to solve this couple problem. This is the difference between the two. So when you get a problem like this, I want to do, well, you know, I can do it, but I need to find out what this force is. First I say, okay, number one, it's a traveling force. Okay, it just moves at a constant velocity. You can do that. But the force itself, and it requires, it's a little bit beyond the scope of this class, but always follow the physics, and you can always model it in as simple a shape as possible, as Jen is learning. Okay, you can have, for instance, a corrugation with a certain wavelength, for instance, and this could be a perfect sphere, and then as you pull it, it bounces. Depending on how fast you pull it, it can track it, and also depending on A versus lambda. Okay, it can follow it nicely, or it can just bounce off the top. And these become sometimes nonlinear problems. They're just solved. So then if it's just bouncing like a fence, okay, then you have little impulses. So when I said at the very beginning, Jen is working on this, where do you think the sound is coming from? The ridges, essentially, okay? See, as you rub, again, if you put cream, you're not going to get the same sound. If you push it hard, and if it's wet, you get these squeak sounds. So they're all different. I had a big project on these before, that's why. But now, why is this important? This is important in characterizing touch, haptics, for robotics, for instance, because you want to be able to pick up something without breaking it. So you need to be able to test. You need to be able to, yes, understand how much force is required to lift it. And so how much should you squeeze it, and so on. But and sound is a way to characterize it, is the way we're looking at it. And for instance, yes, you can look at a surface and you say, this looks like a rough surface. You have a certain expectation. But there are tests that show that in a box, if you put your hand in something extremely soft that you do touch, but you don't know what it is. At the same time, a sound is played, a harsh contact sound is played, your brain thinks what you're touching is actually harsh, like a sandpaper. Okay, and so these are very interesting different research areas that we move on to. Okay, any questions about the relevance of these and all of this? All right, let's move on. I will just start briefly on the radiation problem from cylinders, or in cylindrical coordinates. And I guarantee you'll find this to be much easier because you already know the principles and the difficulties involved in the spherical sources. So this should come to you as a piece of cake. All right. Radiation physical cylindrical. Okay, once again, well-known wave equation. And in cylindrical coordinates, the Laplacian, the left-hand side, is expressed as 1 over r, del over del r. Okay, so the coordinate system phi, r, and z. Okay. We again use the separation of variables for r, phi, z, and time. And of course, as always, each of these functions depend on only one coordinate and time. When you substitute all these, you can separate the variables as following. Okay. Now you can see that on each component is independent of the other ones. So you can equate them separately to separate constants. As far as this portion is concerned, these are constants because there's no dependence, okay? And so we would write this as constant minus kr squared minus kz, and this would be the k itself. And again, for the equality to hold, we would then write kr squared plus kz squared equals k squared. Okay, now, as we see here, both the radial and the angular components are involved, so we will further separate them into two. And Mullah, you have a question? You sure? Okay. Oh, okay. All right. This is need to be written a little bit just to make sure, because I'm using it's both phi, but one is variable phi. So okay. So separating R and phi, we can now write R squared again, we see the left-hand side and right-hand side are independent of each other. And if that's the case, then they must be equal to some constant. Okay. These are the fundamental approaches of separation of variables, some constant number. Now we can express the solutions very simply. Solutions. First, the time. We, of course, use just the A prime. Let's look at Z. If you look at Z here, what you have is that's a simple harmonic solution, right? And you have seen these before, and that is also C e to the I k z z. What does this mean? What is this a representation of?
Harmonic solution.
Yeah. Cosine and sine, but also basically plane waves going in one direction versus the other in z direction. In z direction. Okay. And next, the angular dependence. How should the angle vary? How should the angle vary? Taking a look, quick look. What do you see? Say again? Angle, phi. Yeah, see? Yeah. Right? You're guessing. You need to think. Well, either in either case, sine, cosine, or just the same as exponentials. Okay. Now, finally, we come to the R dependence. And John, you can answer this one. Okay. Well, Bessel functions or whispering. All right. Bessel functions or Hankel functions. So we can either write it as Bessel functions but these are what kind of Bessel functions? These represent the standing waves. Or you can express it in terms of Hankel functions. As progressive or traveling waves. Now, both the Bessel functions and Hankel functions are different than the ones that you saw in spherical coordinates because they were spherical Bessel functions, spherical Hankel functions, and there's a relationship that I gave you at the time between the two types of Hankel or spherical Hankel and cylindrical Hankel functions. Now, how would you obtain the complete solution? You know how to, right? I mean, we have done this now so many times for the spherical case. How would you do that? What would be the general expression for it?
These values.
Yeah, put them all together, basically. Although you have all these different numbers of coefficients, they really reduce to enough number that from which you can find from the boundary conditions. So the solution, as you can see, this is much more familiar to you now that you have done the hard work before. Yes. So the solution, the complete solution in 3 coordinates, just dropping the harmonic time dependence for now. 0 to infinity. Okay, this is the general solution. The ZM1 and ZM2 represent either JM and M or the progressive wave pair. Okay, so I put these in general representation of either the Bessel or Hankel functions. All values of M and Kz are admissible. Now, since you told me that you understood everything from the previous sections, okay, what would be the sound pressure from a cylinder, from a uniformly vibrating cylinder? Okay. See if you can handle that. Yeah, pretty much everything you need. What is the first thing you need to do? Exactly. Express the velocity. What is the velocity expression here? Well, don't look at me. Look at here. What is the key word here? Uniform. Exactly. And uniformly means what? Everywhere it's the same. So times
e to the power minus e times w omega t.
E I omega t. And you had a cosine? You sure? Okay. Now, when you hear the word uniformly, you look at these coordinates. Okay. Where can it be different that it isn't? Okay. You have in this case time. Of course, time has to have this harmonic motion. Then you have z. Then you have phi. Then you have r. Okay. And so it's uniformly in z means what? Up and down, velocity doesn't change. Number one. Okay, so that gives you, if you look at a cylinder, okay, it's vibrating in all directions, but also in the same manner. Now, if this were a pipe, then you would have some bending vibrations. But this is uniform. It's expanding. So there's no z dependence. And the next coordinate is phi, all the way around. We said uniform, so there's no phi dependence. Okay? And what about r dependence? That's the last coordinate. Yes? What is the R dependence? What does it mean, uniform?
I think
This is a trick question, yes.
if we don't, we also don't have R dependence because wherever we go on the surface, it's the same.
Yeah, because we're measuring it on the surface. There is no distance involved. It's R equals A. So, as I said, it's a trick question, but something you need to be familiar with. So, if there is no dependence in angular dependence, M is equal to 0. Of course, Kz is equal to 0, right? Because there is no dependence in the z direction. And what this gives then, Kr is equal to K. It's a pure radial direction, radiation. And if that is the case, how would you write the pressure expression? What is our pressure expression? Take a look at these. There's no angular dependence. M is equal to 0. We have 0 here, and there's no z dependence. If it's just purely radiating, just like before, we would have H very simple. And that would be the expression for sound radiation from a uniformly vibrating sphere, cylinder. Okay. And it doesn't change in the z direction because we're assuming this is infinitely long in z direction, otherwise there would be a z dependence. And it just radiates out. And this is very similar, analogous to the spherical case, but this was different. It was a spherical Hankel function. You can see the analogies between the two. Any questions? Yeah.
Is this KRR or KI?
I just erased, but because this is 0, it becomes KR, okay? Very good. You need to keep in mind that, yes, these are all different types of, different components of the wavelength. But in this case, it becomes exactly the same, yeah. All right. If no questions, I will see you Tuesday, and if there are any changes in the scheduling, I'll send you an email, okay? And then I'll ask you what your schedule is like. Thank you.